Well, looks like we can start. Welcome back, everyone. And again, excuse me, happy midterm week. We're at the halfway mark so far. The big announcement is the upcoming exam two. The coverage is going to be these sections right here. Bigger emphasis really on these sections on logic that we were covering in chapter 3. But for the problems in section 2.5 on functions, it's going to be just a couple quick questions, maybe a domain range question or a one-to-one onto kind of question. Just like before, this is going to be a resource provided on the last page of exam 2. And it's a good idea to, when you're practicing the exam, studying the problems, have this pulled up just so you can know where everything is, how to work that formula sheet. And it'll also inform you on the things that you have to have memorized for the purpose of the exam. Then I have two different versions of the sample exam 2, pretty much parallel to the formats that we did in the last exam 1. These are the lecture notes converted into essentially now worksheets. And these are brand new problems that have the solutions at the very back. For solutions here, just go to the section that it's relevant, and in the Canvas notes, you'll find the particular solutions. Well, any questions at the moment, folks, with the exam 2? Okay, as far as the exam goes, just for advice on studying, just like we did for exam 1, because we don't have a review day built into this class, I try to make it so the exams are pretty in line for what we actually did in class and what you also actually did in the homework. So that means if you're behind on any one of these sections, the very first thing you should do to get prepared is get caught up with those, turn them in, and I'll be trying to grade these as fast as possible to get you your feedback. Then after you're fully caught up on homework,
Professor,
turn to, yeah, go ahead.
I have a question. On the first exam, I tried to bring my pencil case, and they were like,
Hmm.
that is not allowed, and you would have to ask your professor next time. So I was wondering if that's allowed at all, or.
I don't see why that shouldn't be allowed. I mean, if you have multiple pencils, multiple colors, I think that's a great way to do an exam. Was
I,
this the Pocatello or Idaho Falls Testing Center?
it was the Pocatello one, and I think they said that if it's allowed, that the professor has to kind of write a message to the center that we're allowed to have it.
Gotcha. Sorry about that. That's kind of frustrating to be have materials like that turned away, but I don't see why there's any problem. So I'm going to write to the Pocatello Testing Center and say people are allowed to bring as many writing utensils as they would like, in an entire case if they prefer.
Okay,
So
thank you so much.
yeah, you bet. Thanks for mentioning that. Write to the Pocatello Testing, once I spell that right, Pocatello Testing Center. Students may bring as many pens and pencils as they choose, as they wish, probably is better wording there. And a pencil case is fine too. I won't worry about the grammar spelling at the moment, but I'll send off that message as soon as possible to make sure those materials are in fact allowed. Other questions at the moment? Okay, and again, sorry about them being kind of strict. That's kind of surprising. I never heard of Hotel Testing Center doing that before. Probably they've been doing it all along. You're the first one to bring it up, so thank you for mentioning that. I'm going to try to, when I schedule the exams in the future for the Pocatello Testing Center, to just write that into the proctor form so that it's going to be less of a worry. Well, any other questions at the moment, folks, about the upcoming exam two? Yep, you bet. Okay, well, as far as the coverage goes, it's going to end at section 3.5. We're starting the section 4.3, and we'll probably complete this one this week. We'll see how the pacing goes. But this material is now turning over to what's going to be on the third exam sometime after spring break. So here's where we left off on. Well, we didn't get too far, actually. We just started highlighting things. We brought in this table here for the truth table for the implication. And we're looking over what do we mean by a proof, a convincing argument, and what a direct proof is really going to look like. When we're thinking about a direct proof, we're going to start from known facts, say, for example, these definitions on what it means for an integer to be even versus an integer to be odd, do some work, define variables, quantify things as necessary, and try to arrive at the conclusion, which is going to be in this setup, phi. You know what? Yeah, the conclusion phi for the proposition. So in this problem down below, we're going to prove if n is odd, then the square of n must also be odd. Essentially, we're looking through this truth table right here, and in our direct proof, we're going to assume immediately the proposition p, n is odd, and try to resolve that to the proposition q, n squared is odd, as our very last step. So essentially, this is the direct proof right here. Really just using one row of that entire truth table is our direct proof. Provided the statement has the structure, if P then Q, like we wrote here on the implication. So here's our two basic facts. We looked at this briefly, I think all the way back in section 3.2. The essence of an integer being even just means it's twice some other integer. So if you can double something, it means you can also divide it by 2, and you have an even integer. So the essence then for an integer being odd is start with something even and add 1. You could have said subtract 1, that'd have been a fine definition as well, but we'll stick with it in this form in the notes. So armed with these known facts, this part right here in the direct proof, we're going to start by assuming n is odd, that's the proposition p, arrive at the conclusion n squared is odd. Before we even get started though, this is a pretty direct replication of how a lot of the homework exercises go. We want to quantify the statement just to get another take on this, another view looking at it through the lens of logic instead of ordinary words. Then we'll directly prove it in part B. So this is kind of nice as well because this is really just a review on quantifying statements like these. And if then statement, this is kind of surprising and it came up in the homework, is really a for all quantifier. We want to say for all integers n. So for all n in the set Z. Now we're going to write out the P implies Q portion. We'll say if, rather using if, I'll just go like this. N is odd implies n squared is odd. So that's the entire quantified statement. Really all we've done is switch out if then for the implication, so that wasn't a big change. We're also taking a different view. This statement here really involves the universal quantifier at its heart. So we're trying to prove this statement for every single integer n, provided if it's odd, the square of it must also be odd. Well, that's our start so far. Any questions at all, folks, with the quantified statement? Okay, well, here's really our second proof for the course, but when you think about it, we've been proving a lot of things in the last chapter. We've proved lots of logical equivalences, and they'll come back in these notes and various exercises as we get through them. To prove this one, we're going to start by assuming proposition P is true, so let's go along those lines. For the proof, assume n is odd. So we take in the truth, value of true on this proposition P. We must arrive true on the proposition Q, n squared is odd. But one thing we cannot do is say, write down n as 7. It's not wrong in the sense that 7 is an odd number, and if you square it, you get 49. You would arrive at odd. The problem is we're trying to prove a universally quantified statement. So we can't assume any value whatsoever on n. We can't pick an integer like 11, 1001. None of that's going to work for us. if we're trying to work with every possible odd integer. So instead, we go here. Because we assume that n is odd, and we're going to allow n to be a fully arbitrary odd number, we now need to say, what does it mean for it to be odd? Here's where we're quantifying the new variable. If n is odd, we have to say n, let's write it out this way, there exists k in z such that n equals 2k plus 1. So here is what it means for our integer n to be odd. I'll say here just to write out an ordinary sentence. After we said it's odd, then we get this existentially quantified statement. And that's what this is again talking about right here. We can't just say this part, n equals 2k plus 1. Much like it's say in a coding language, similar with writing down a proof, every variable has to be somehow declared. We didn't say what k was at the very onset. We have a flaw in the proof. We're thinking in terms of coding. The code isn't going to run well. So when we say quantify all variables, we mean this part right here. For a full credit on a proof, whether it's a homework assignment or exam question, we must quantify the variable k. So we had to say this part right here. Where did k actually come from? You didn't necessarily have to use this structure. You could have said, then there exists, in ordinary words, an integer k such that n equals 2k plus 1. But this is just a compact way to say it altogether. So we're still at this part. We assumed odd. We wrote down what it means. We quantified where k came from in the same step as well. Now we're showing all logical and algebraic steps to try to arrive at n squared. So if we have n right here, we can go ahead and square it and just see what happens. So let's let that be our next step. I'll say next, n squared. Recall, we're trying to arrive at odd for n squared, which means we're trying to get this to work out once again. It's going to be a different integer k, but if we can find that integer and write n squared in this format, our work is done. So take n squared, it's going to be equal to the square by substitution of this value. Just throw in the 2k plus 1. Square this out, and we're going to get 4k squared plus 4k plus 1. So there's our n squared. Again, we need to fit it into this formula because we're trying to assert n squared is odd. It's almost there. We have the plus 1 that we're trying to get. So we're matching up with this part. It needs to now be double some integer k. We have to show all algebraic steps. So this is the next step we have to show. From the very first two terms, if you factor out, say, 2, you're matching up that part of the definition of oddness, and you get 2 times 2k squared plus 2k plus 1. That, it's just a different algebraic form of n squared, but this is now extra special for us. We can fit it into that structure. We're going to take our k to be this right here, but we need to be very, very careful. We also have to be sure our new k is really an integer. So that's the next line of the logic. Oh, sorry, I'm not sure what I did there. Let me go back. We can say, I'll go with the uppercase k, be equal to 2k squared plus 2k. Now let's think about where little k came from, lowercase k. It was an integer, and integers are closed under the operations of addition, subtraction, multiplication. That's multiplication there, but not division. So if I had a division here, I'd be really worried. If it was divided by 7, that's not a guaranteed integer any longer. But this is automatically an integer. So we can say, let k be equal to that. I'll go with the period after all. Then K is an element of integers, K and Z, since we quantified lowercase k. So now we're saying at this sentence, if we take an integer, double it, or square it first, then double it, then add twice that same integer, it's still an integer. What does that get us? We're back to this right here. We found an integer, k, that's our uppercase K written down below, such that if you double it and add 1, it resolves back to the original n squared. What does that mean about n squared? It fits this structure. We can now just conclude right here, state our conclusion. N squared is in fact odd because it fits this right format. I'll say it this way. Then n squared is equal to 2 times k that we just produced plus 1, which means n squared is odd as required. So we got through showing all the logical algebraic steps. The last thing we had to do was show our conclusion, and that's what we said right here. So this is now a long argument that started with the left-hand side of the implication. All we were armed with was n is an odd integer. Then we went to the definition, wrote it as 2k plus 1, but critically we have to say where every variable comes from, much like this right here for k, we said it came from the set z. We did some algebra, we worked out some more logic, and we arrived at this. That's our conclusion now. N squared is odd. So we never assumed a value from n, we just assume its oddness. We have now proven this universally quantified statement. Any odd integer you pick now, we know the square of it must stay odd as well. And the details are everything we said down in the middle. Well, any questions at all or comments, folks, getting through that proof? Okay, we're going to practice a lot more because just doing one problem is not a good idea. So for every new proof technique we look into, we'll do at least a couple proofs on them. As far as this goes, the proof statements we're trying to prove, they're not going to be huge mathematical statements. Really, we're just trying to focus on the logic, the structure of what a proof would look like on each one. And so that's kind of what's going on with the next one. It says, prove that the product of any two odd numbers is odd. This is a statement that we quantified in homework, so we'll do it again and see how it goes. But once again, we're really just using the same kind of tricks, work through trying to prove this implication. So let's try this out again. Prove the product of, now we have two odd numbers, and it has to come out as odd. So since there are two numbers we're working with, two integers, we can start by saying, for all, let's go maybe x and y. For all x and z, next, we have nested quantifiers. For all y and z, these are odd numbers. So let's just say this using ordinary words. I'll start with brackets and organize like this. X is odd, and y is odd. So if we start with two odd integers, the product must then be odd. So this implies x times y is odd. So that's from our section 3.5 homework assignment. Now we're going to prove that this is an actual mathematical fact. And again, we can't take a number like, say, 5 and 7. The product is 35, it's certainly odd. If it was false, we would have disproved the statement. We have to let both x and y at the same time be fully arbitrary. So we just go back to these definitions to work through. Well, any questions with the first step, folks? Just quantifying the statement above. Okay, let's maybe just screenshot this into the problem to refer to it a little bit easier. That's way too big though. Let me fix that. Okay, so above is the statement in ordinary words that we want to prove. Below is the quantified statement. It definitely looks messier when we quantify it this way, but it tells us essentially what are we doing really. It reminds us that there's an implication in the problem. So we're going to start using the same kind of organization. We're going to assume we have two odd integers. Then our goal is to end at a conclusion. The product of those integers must be odd as well. So it starts by assuming this part, P, is actual truth. Assume, I'll write here just because it's a proof. It's standard to start by saying proof where your argument begins. Now we'll say assume X and Y are odd. We have to now write down, what does that mean? That means you can write out X equals 2k1 plus 1, Y equals 2k2 plus 1, but we can lose some credit if we just leave it like this. Once again, we must quantify all variables that we define. We said what X and Y are. We said they're odd, so that implies we're talking about integers. That's where even an odd comes from. We're dealing with integers. But we also declared new variables k1 and k2. We have to say what exactly are those. So going back to the definition, for odd, right over here, we needed to put at the front, there exists k1 in z. That's a subscript 1 there, I forgot. So now we know that's an integer, and we also have to say directly, some way, shape, or form. This is just a compact way of saying it. There exists a k2 in z. So we have two different integers. X is equal to twice that integer plus 1, and similarly for y. So that's just assuming this part is true. Written down algebraically, we have these two forms of odd integers. Now we're ready to try to get to this conclusion. Any questions with this step here so far? Okay, I put in just extra words. It's nice to try to make your argument kind of flow like a sentence. I was writing in, well, I forgot, then I wrote in, then we have this for some k and z, x is 2k plus 1, and just a comma. Exists another k and z, y equals 2k plus 1, period to end that sentence. Now we go to the next bit. Next, we want to see what happens to x times y. At this stage, we're now showing all logical, all algebraic steps. When we take x times y, not too different from what we've done before, we can put in 2k1 plus 1 in place of x, 2k2 plus 1 in place of y. You didn't have to do k1, k2. You could have went to j and k if you prefer. But keeping it as subscripts, we're now dealing with the k1s and k2s. Expand this, we'll get 4 k1, k2 plus 2k1 plus 2k2 plus 1. I recall we're trying to get to x times y to fit the format of an odd integer. This part is checking out already. We have the plus 1 right here. We just need to double something that we know for sure is an integer. Same trick as before. If we factor out 2 from now the first 3 terms, we'll have an integer hopefully left behind that's being doubled, the 2 part here. So let's keep on going. xy is now equal to 2 times k1 times k2 plus 2k, rather plus k1 plus k2, forgot how to factor out the common factor, plus 1. So now we have this part right here. The last thing to worry about is that guaranteed to be an integer? And it definitely is. We quantified k1, k2 as integers, just like before. We have closure with multiplication and addition And subtraction, if it came up, you can multiply, add, subtract integers in any kind of configuration like this. It's still an integer. We're just worried about division. So if I had a division here, that could be a major problem. But because it fits this format, we could do what we did before, redefine this as an uppercase K and just fit it here. Or we can say, here's just a different way to go. XY equals this. And so XY is odd because K1 times K2 plus K1 plus K2 is an integer. Or we could have said is an element of Z if you preferred. That's probably a faster way to write it. No harm in just using ordinary words occasionally, just to cut down on the amount of symbols we see. But we did it, folks. That's essentially the end of the proof right at that step. We started with two odd integers, we multiplied them together, and that's the format for the odd integer, their product. Yeah, I'd be happy to. Let's run through this again. Thanks for asking about that, Sophia. So the way this one's going to flow, let me kind of reorganize this window right here. Let me see if I can put, yeah, sometimes it doesn't always all go down. We hit enter there. So here's the flow of the proof. It's taking a step back and looking at it from an element by element basis. We were to prove that the product of any two odd numbers is odd. And this was the critical word right here. Any two odd numbers meant we had to say for any x, for any y, we have to make them both be odd in this statement right here. So I use the logical connective and to bring those two pieces together. If those are both odd, the product is also odd or is just odd. So that's this piece right here. So when we went from here to here, that's the statement quantified. And now the major thing we're focusing on is, can we prove this when we don't pick a number for either x or y? We just say they're odd. And now they're fully arbitrary odd numbers. They could be, say, to the power 1000 plus 1. That's one odd integer. And y could be something weird like that as well. Or maybe it's just -3 as an odd integer. But once we said this part right here, we got through the universally quantified statement. What we have to now look into on the next step, what do we mean when we say odd? We have to write that down. Odd means this. Let me just focus on this part right here. The existence of an integer such that your number, we put x and y in this spot for n, your number has to be double that integer plus 1. So that was the assumption we put here in the quantified statement. But because we're dealing with two different numbers, we had to say two different integers as well, a k1 and a k2 value. Notice if we didn't do that, our algebra down below would be very, very different. So x is twice some integer, add 1. Y is twice some other integer, add 1. And that got us through this entire statement right here. Does that make sense so far to this stage of the proof? Okay, let's turn into the next stage. We're trying to arrive, now that we have two bona fide odd integers, fully arbitrary. We didn't say which odd integer whatsoever. We're trying to land on this conclusion. Multiply them together, prove they are absolutely another odd integer, x times y. So let's take a look into that next level. The next thing we said is look at x times y with the goal of showing it's odd, but let's just look at the product first. We made two substitutions coming from what x was defined to be, what y is defined to be, expanded it, they came out like this. Kind of an ugly algebraic form, but it is what it is. It's all based on the original statement. But we could take another interesting step once we got there. Once we got to this line right here, notice if you factor out 2, something kind of magical happens. With this 2 right here and a +1 right here, we have matched these two elements of what it means for an integer to be odd once again. So all we needed was some value k that's definitely an integer. That's what this is. Now, for example, just for sake of what could go wrong, if I made some weird algebraic misstep or just set something up in a weird way, and I arrived at, say, instead of what's highlighted yellow, maybe it was k1, k2 plus k1 divided by k2. Now I've got a really big problem because this is not going to be in the set of integers for every possible combination of k1, k2. And k1 and k2 are fully arbitrary, just like x and y are arbitrary at the same time. So this is not guaranteed to be an integer. If, say, k1 is a 1 and k2 is something like an 11, then we'll have 12 divided by 11. That's in the set Q, not in the set Z of integers. But this is fair game. If you start off with integers, any multiplications you do, whether you're raising them to power 2, anything you add and subtract, you're always going to result in another integer. Another thing to watch out for is you can't have anything like this, square root k1, k2 plus k2, and so on. Square rooting your combination of integers could be a non-integer. 5 is an integer, but the square root is not. So if a square root came up algebraically, we're still in trouble once again. But once we got to this statement right here, we very carefully looked at what does it mean for something to be odd. There's the existence of an integer k, such that if we double it and add 1, we're back to odd. That's what we were trying to show. The product x times y is odd. And so once we got to that step there, we made this statement. xy is odd because k1 times k2 plus k1 plus k2 is an integer. When we said that, we were just looking at this part right here specifically in the definition of odd. So from top to bottom, this is the logic on this one particular direct proof. These are tricky, so I appreciate the questions on these. The one thing I could be really bad about the 4.3 notes is if nobody has any questions whatsoever, then we get through them really fast, but that's probably not the best use of class time. Yep, you bet. Any other questions at the moment, folks, getting through these steps? Okay, and again, the grading on the homework is going to be kind of picky on certain things. Just for another emphasis, we absolutely have to say where every variable comes from, what it represents. So x and y were the first two variables. When we said they're odd, we're also implying they're integers. So we didn't have to be as specific about that. But when we wrote x is 2k1, 2k1 plus 1, y is 2k2 plus 1, we were required to either, you can say, quantify or define the set that both k1, k2 came from. I'll say just quantify for short. Required to quantify k1, that's a 1, and k2. Subscripts are kind of annoying sometimes. So that was the issue with quantifying the variables. Showing all logical steps was pretty much us saying, assume the hypothesis right here. We had to actually say that at some point. That was a major logical step. As far as showing the algebra goes, we have to show these steps, but that's usually the easy part of the notes. That's just ordinary algebra. Then we had to arrive at this statement because that connects the hypothesis with the conclusion down below. And finally, when it says clearly state the conclusion, that would be both this part right here, stating xy is odd, but also we have to state this part. those go together in the conclusion. It's odd because K happened to be in Z in the first place. So those two pieces are really part of the overall conclusion. We found the integer, therefore xy is odd itself. So we'll go through these different elements on every one of these proofs that we go through, just to make sure we're hitting all these things. And if, let's say you're doing a homework assignment and you missed a bunch of them and you say lost out of a 5-point problem, lots of the points, I'll give folks in this assignment an opportunity to just rewrite their homework assignment based on the comments I give. Because this sometimes is really tricky to get down pat on your first try. I'll give lots of comments when I grade these and give people opportunity to rewrite to make up credit if a lot of these steps were missed. Well, that's 2 proofs down. Let's see what's coming up next for the next ones. These were both direct proofs, and the next type of proof we can give is called proof by cases. Before we look into that definition, it's interesting to know when a proof by cases really comes up. Take example 3. It says, for every integer n squared plus n is even. And let's pause for a moment. Why is this a hard one to prove if all we're reusing is the tricks in the last 2 exercises? It's because we can't use these definitions at all to start it off. It just says for every integer. It didn't say n is even. It didn't say n is odd. There's no information whatsoever about the parity. We have to arrive somehow at n squared plus n is even. That looks like it's going to be tricky to get there. That's where proof by cases comes into play. This example 3 is really 2 proofs just sort of duct taped together by different cases. The definition says, to give a proof by cases of a proposition phi, that's the whole proposition phi right here, we identify cases and then prove 2 different types of facts. Well, here the cases we're going to use on n is that if we say for every integer, well, n could be positive or negative. Those are 2 different cases. But positive and negative don't really fit into terms of even and odd. It has nothing to do with it, really. Even and odd have everything to do with those 2 equations we see here. So what are other cases? Instead of positive or negative, we can say, how about even and odd, like we were mentioning? Those are 2 different cases for an integer n. We have to prove the statement is true in every case that occurs. So we must prove n squared plus n is even in case 1, n is an even integer, and then in case 2, when n is an odd integer. And we have to also justify or prove every one of those cases has to occur. Usually this is not the too bad part, but that's how proof by cases is going to go. Once again, it's not a massive mathematical fact. We're trying to focus purely on the logic, more on the proof technique, not get lost in the weeds with a big statement, like say fundamental theorem of algebra, or worse, the fundamental theorem of arithmetic is a tricky one as well. Well, any questions at all, folks, about the definition before we give it a try? Okay, well, here's our statement. For every integer n squared plus n is even. Just like before, just to get a different view of what's going on here, we'll look through it in a different lens, using logical connectives and quantified statements. But this one's not so bad to quantify, where it says for every integer n, we can just write down verbatim, for every n in z is now saying for every integer n, and that's that whole first part right there. N squared plus n is even, I'll just write in as n squared plus n is even verbatim. So part A wasn't really a massive shift in point of view, other than it reminds us we can't pick an integer. We have to do this for fully arbitrary sets of integers. And again, this is where proof by cases comes up for us. This is a really hard statement to prove without having any algebraic hook to work with on n squared plus n. I can't factor that or do anything with n squared plus n to make it fit this structure. the essence of an even integer. So we'll do this instead. We're going to make a big assumption on n just so we can get us started. Let's say proof by cases. First thing I want to look into on the proof by cases is this part. We're going to say every one of these cases has to occur by labeling the cases to start. Let's say assume n is an arbitrary integer. Or we could just say assume n is any integer, verbatim of what we said there. Then n is either even or odd. And that's a mathematical fact I think everyone will believe. We have a nice dichotomy of numbers, integer numbers. They're either even or odd, and there is no middle ground. 0 is even, for example. You can get zeros even by picking k to be the 0 value right there. So we're going to use both this statement, what it means to be even, and this statement, what it means to be odd. But we must conclude that n squared plus n itself is even when we work through the cases. So we've identified two cases, and we absolutely do know every one of those cases, at least one of those cases has to occur for any choice of an integer n. Well, any questions so far, folks, before we dive into the cases? Okay, well, let's start with say even because it's right here on the paper. Let's say assume for case one, let's label our cases as well. Case one, assume n is even. The moment we said that, we have now an algebraic form we can write down. N equals 2k, but we must quantify where that extraneous variable k came from. N was already defined right here when we said it was an integer. So we need to say next, then there exists k and z. We have the existence of an integer k such that n equals 2k. So once again, this is all what it means to have even. Now we have to come back here. We need to now show next n squared plus n is even. But that's not so bad. We have something to work with algebraically. We can substitute inside here 2k and square it, add 2k. So that's our next step. We can say here, then n squared plus n is going to be equal to something squared plus something. But we now have a form to write n in. It's going to be written in as a 2k on both of those spots. At this stage, it's flowing just like example 1 and 2. The only thing that's really new here is we had to tack this statement on a proof by cases. But square this, we get 4k squared plus 2k. Then if we factor out, say, 2, we're left behind with 2k squared plus k, but this is what it means to be even. We have something doubling what we know to be an integer because we started with k itself being an integer. So this line right here now tells us n squared plus n is in fact even. But let's focus on that. Even meant that this part right here was an integer and you're doubling it at the same time. Double any integer is automatically even is the logic with that equation. All we have to do is write down that conclusion. This shows n squared plus n is even. That was weird. That kind of updated slowly. Is even because 2k squared plus k is an integer. I'll just write it out this way using the set membership condition. If we can get to this statement right here, finding an integer that got doubled, which is equal to the original n squared plus n, we arrived at evenness. Well, any questions at all, folks, getting to that step there? Okay, well, let's try this out again. The proof is halfway done. All we now know is if we square an even integer and add that same integer, it results in even. But this said for every possible integer. So that's why there is a case 2 next. We're going to say for case 2, now assume n is odd. So when we assume n is odd, we have this definition for even, but now we're going to this definition. We need to take an even integer, that's the 2k, add 1, now it's automatically odd. So we just have to quantify that, state the definition. Because we said n is odd, we can now say then n equals, let me write it this way, then there exists k in Z such that n equals 2k, add 1. Notice I used k again on case 2. That's kind of weird and it might feel a little bit funny. So if you call this a k1 and a k2, I'd say that's totally fine. But if you left this as k, that works as well because we think of case 1 as being an entire universe. It's an entire argument that ended right here. In other words, this k value is not in the same scope as this k value. We're just redefining it for a whole entirely new argument. So these have nothing to do with each other. We can just reuse that variable. But again, if that just feels weird, if it flows differently for you, you can go say maybe k, maybe j, some other integer you'd like to define, and that'd be fine as well. But once we have this down, we go back up here and we just redo the algebra. We have to take n squared plus n and show it comes out as even. Let's say then n squared plus n, here's the algebra part. We're going to take something squared, add that something back to it, make a substitution 2k plus 1 in both of those slots. The odd integer case is definitely a little bit more messy, but let's get through this algebra. We're going to arrive at 4k squared plus 4k plus 1, then copy 2k plus 1. So now we have n squared plus n is equal to, combining our like terms gives us 4k squared plus 6k plus 2. All the coefficients here are even. That means we can pull out a greatest common factor of 2, which is exactly what we want to do. If you can place a factor of 2 in front of some integer k, whatever it happens to be, no matter how messy it is, you have shown it's even. So let's factor out that 2. 2 factors out, leaving behind 2k squared plus 3k plus 1. And that's exactly this format for an even integer. We just need to state the conclusion on this stage here. But any questions at all, folks, getting to this step? Okay, so once you get to this step, there's different routes you can go. You can redefine this as, say, maybe uppercase K, assert that it's definitely an integer. Then you have that the n squared plus n portion right here comes out as even. which is the major conclusion we were trying to land on both of the cases at the same time. If you want to go just a little bit more brief, you can say, this shows n squared plus n is even because 2k squared plus 3k plus 1 is an integer. So the thought connecting there is we doubled an integer, and the moment you double an integer, back down to this definition again by the red dot, you can assert the original thing you're working on, n squared plus n, it had to be even. There's no question about this. No argument we can make to the contrary. This is the essence of an even integer. No matter how crazy it gets here, as long as that thing on the inside of the parentheses was an integer as well. Well, we're done. We've argued that either case can come up. In both cases, we landed on a conclusion. N squared plus n is even. Here's the conclusion here, n squared plus n is even. That's a conclusion here, n squared plus n is even. And so this is the end of the proof. We can say, for any case, n squared plus n is even. In other words, it didn't matter what case occurred for n. Pick n to be an even integer or pick n to be an odd integer. We can always conclude n squared plus n came out as even. Here's the assumption that it's odd there. It's a lot to look at when it's all completely on paper. That's the downside of the proof by cases. If there's a way to get away from proof by cases, it's always the best thing to try. Because if I had, say, some other situation with 5 different cases, then you have to give 5 different arguments and so on. But every single one of these was just a direct proof. So now we're seeing how the new proof technique kind of just interlaces with an old one. And that's a theme for these proofs as we get further and further on the notes. Any last questions or comments at all, folks, on getting through this one? Okay, let's, again, because these are tricky problems, this can't be our only proof by cases example. We're going to try it out again. That was way down there on the page. There it is. Again, my mathematical facts here are mostly pretty basic statements that you probably believe already when you look at them. I think most people can be convinced without saying too much. Surely x is always less than or equal to the absolute value of x. But now showing the details is surprisingly tricky. It won't be too bad when we see the whole thing on paper, so we'll get through this carefully like before. But here's another interesting mathematical fact. Here's where it gets pretty interesting, where we need just other ideas, proof by contrapositive. Here's a statement that says, take any 2 real numbers where the second one is non-zero. If x divided by y is irrational, then x is rational or y is rational. And I think a lot of people would believe that. If I take a real number like 5, divide by, say, square root of 2, then one or the other, if the whole division is irrational, one or the other had to be irrational. But in its form, that's a pretty hard proof to get through. So we'll work it with a proof by contrapositive, probably when we come back on Thursday. But for now, let's try out another proof by cases statement. It says for all real numbers x, any one whatsoever, we're not talking about even and odd any longer, we have x must be less than or equal to the absolute value of itself. Well, first, just to get a different view on what it's saying, we'll quantify it. This is another fast one to quantify. For all x and r, we just rewrite as for all x in the domain of discourse, the set of reals. We have to have this equation, x less than or equal to x. Essentially, in a certain sense, what we're doing is we're just going back to sections 3.4, 3.5 on predicates. Here's the predicates right here on quantified statements and sometimes nested quantifying. We saw these kind of statements before, but now we want to prove them. So that's what we're going to do on this one. This one's tough because, again, I can't just pick any particular x whatsoever. I don't want to worry about even and odds. It doesn't really fit into this picture. But there's other cases we could do on this one. And here's the motivating thought about this. There's lots of ways to define the absolute value of x. You can think geometrically. It's the directed distance on the number line from the number x to 0. Or you can think algebraically. Absolute value of x is the square root of x squared. So here's the algebraic form. Or you can think in terms of functions. Absolute value of x as a piecewise function is defined to be x in the case x is greater than or equal to 0, or negative x in the case x is less than 0. And these are meant to be commas right here. I like this because if you see a piecewise function, it's automatically telling you cases. Here's how absolute value is defined. In case it's non-negative, it's itself. And in the case it is negative, it's the opposite it's the opposite of x. So using that intuition, we automatically have a proof by cases set up. So we'll start off by saying proof by cases. We need to argue either one of these cases must occur, but that's pretty fast. We can say for any x in R, x is either non-negative. That's the first row. X greater than or equal to 0 is just a different way of saying non-negative. Or it is negative. We know intuitively that's a true statement about the real number system. There's no middle ground here. If we're talking about negativity, you're either negative or you're non-negative. So that's our two different cases in the absolute value function. Now we'll just look into each statement. We'll start maybe with non-negative, then do negative as the second case. But we have to prove the original inequality, this right here, in both of the cases. So we'll say here to start, case 1. Assume x is, let's write out this way. I want to assume x is non-negative. But let's use this form. Assume x is greater than or equal to 0. I think that's a better way to start. So we've assumed the non-negativity there. We now need to prove this inequality. But you know it's not too bad because the moment we made this assumption, x is bigger than or equal to 0, we can say, then absolute value of x, see the piecewise function, that's equal to just x. Here's another thought, though, that can make this a little bit confusing on the next level. That's really a logical connective that's hidden inside there. X less than or equal to x is equivalent to the statement, right? Rather, I should have said x less than or equal to the absolute value of x is logically equivalent to the statement x equals absolute value of x. Wrong direction. That looks like an and. I meant to say or x is strictly less than absolute value of x. Because this is a conjunction, an or statement, if you show one or the other, the total statement up above is true. So that's just our truth table coming from way back in the day, 3.2. There it is, finally. Here's the disjunction. If you show just one is true, this would be the P, or the other is true, this would be the Q. You have truth on the entire statement, x less than or equal to the absolute value of x. So with that in mind, the moment we said x equals, or excuse me, absolute value of x equals x, that's the statement. Let's just turn this around. In other words, we wrote x equals the absolute value of x already, but this is just a different order. So we can relate it back to the original inequality. Implies automatically x is less than or equal to the absolute value of x, and our work is done on that. We assume non-negativity, and we arrived at the inequality we want to show on the onset. So case one looked like it'd be weird, but that wasn't much to write on this one. We just have to think in terms of what do we really mean by the inequality, the or statement really, get one side or both true, and our work is done. Any questions at all, folks, with running through case one? Okay, certainly the interesting case is this one. It's either non-negative or it is negative. We look into case two and apply the absolute value function. We're going to get this output, but really it's not too bad either. Let's write this out as case two, assume. Now negativity, just written this way, x is less than 0. If you make that assumption, then you can rewrite what the absolute value of x is by our definition above. We'll say then the absolute value of x is the negative of x. It makes sense, right? If x is negative, the absolute value cannot be negative, so we put in a double negation right here. You just don't see it because there's only one negative sign, but also the assumption x is negative. Then what should we do from here? Well, if absolute value of x is equal to negative x, and x was negative, well, we can then say, then let's place our negative x right here. Negative x is going to be equal to, let's say, hang on, I think I'm getting mixed up on the logic on this one. What should we say next? Let's think about this one. I have absolute value x equals negative x. I want to show, I think this is where was getting mixed up. I was trying to place a negative x right there. You know, the argument is on x itself, so I should write x to start. So I want to relate this x back to the absolute value function, and there it is. So I need to relate my x I put down on paper to negative x. And what we can say for sure is x is less than negative x. Easy for your head to spin on this logic, so let's see if it makes sense. On the left, recall that that's negative. We assumed it, x less than 0. On the right, well, negative of a negative number is now positive. So that's a bona fide inequality. It's a strict and true. A negative number is strictly less than a positive number. But then we could say, hang on, we're using the absolute value function. We're in case 2 right here. Negative x is in fact absolute value of x, so we can relate it this way. That's this part we just shown. We showed just one side of the less than or equals to, but that means the whole thing is true altogether. We can now take this together and say, this implies x is less than or equal to the absolute value of x. It's certainly not equal to it, but that's an or statement. We show this is true. We showed x is less than x. And even if you put a false statement there, that's okay. The whole statement is true with the disjunction, the or statement. So the moment we show the less than part, that flips true. And the whole original thing that we want to show is true as well. So we landed on this statement on both sides. Let me just write it in a parallel way. This implied that x is less than or equal to absolute value of x, like we showed right above. So now our work is done. In either case, whether the integer was positive, non-negative, we did put in a case of 0, whether it was non-negative or negative, we showed x is in fact less than or equal to the absolute value of x altogether. Somehow this one was the tricky one for me to go through. And some people might have attacked this differently. Some people might have said, go for a trichotomy, 3 cases. Assume strictly positive, Now in case 2, assume x is 0. And then on case 3, assume x is less than 0. And that would have worked out just fine as well. We went for 2 cases because this is a typical way absolute value is defined in the first place. Sometimes some books have strictly bigger than 0 here, less than or equal to 0 here. That's immaterial which one has the or equals to. It's the same exact function. Well, that's 2 different takes at proof by cases. Any questions at all, folks, proving this fact here? Okay, again, so far, these are all just pretty standard mathematical facts. Some of them, like this one, we possibly take for granted on an ordinary basis. But if we ever had to say exactly why something is true, that's where this structure is helpful. Now we're going to turn over to proof by contrapositive, where sometimes things just get a little bit messier. Like this statement right here. This is somehow just not an easy statement to prove whatsoever. But I think a lot of people would agree. If you divide 2 real numbers and the denominator is non-zero, so it's defined. If you divide 2 numbers and you get irrational, either the numerator or denominator should have been irrational. Yeah, absolutely. Any questions on this page so far? Yep, absolutely. Thanks for asking about that. Sometimes it's tempting to scroll a little too fast on the notes. And again, this problem is kind of exciting because it's a hard one to break open. It's at its heart a direct proof. There's an if and then statement, but this direction is really tough. Also, we're talking about specific sets of numbers, taking us into section 2.2. We're talking about irrational numbers, and as a set, notice we didn't even try to write down anything. We just said I is a set of irrational numbers, and all we mean by that is not rational. That's all we really are saying in these notes. Did we say that at some point? A real number that's not rational is an irrational number. That kind of leaves a lot to be desired when it comes to irrational numbers. But this set is a lot more complicated than you would think. It is got a lot of structure going on, a lot of interesting topics come up just on that set alone. If we can relate it back to the rational numbers, there's a form, much like there's a form for even and odd. If we say a number is rational, we can write down a fraction, quantify the numerator variable and denominator variable in these 2 different ways. And now suddenly we can do something algebraically with that. So that's how the contrapositive enters into this problem. And just for a reminder what we mean specifically by contrapositive, let's go back to, I think this was 3.2. Was it? Maybe. Oh, I don't think it was. It was 3.3, I think. And it's somewhere up here. There it is. Here's our contrapositive. Because I have to take that whole thing based on the way that was written down. Okay, so this is a structure we worked really hard on when we were way back in section 3.3. We have the implication, P implies Q, which is essentially this entire statement right here. Above is just, or to the left is just where the variables X and Y are coming from. The major part of the proof is proving that. But that's a tough proof, so we looked into the contrapositive. And I regret my highlighting. I wish I'd left it like this. Let's focus on these 2 portions. The implication, P implies Q. Let's just undo that. And the contrapositive, not Q implies not P. We check those truth tables, truth values again. We notice they match up. True to true, false to false, true and true to true and true. What this means is P implies Q is logically equivalent. There's our triple equality there. To not Q implies not P. We made a big deal out of that because if we can take an implication like this one, because it's logically equivalent to the contrapositive, if we can rewrite it as a contrapositive and prove the contrapositive through the logical equivalence, we've proved the original statement. So this one, I don't even know how I would get started proving this one, but the contrapositive is much, much more direct. Let's maybe do part A, just writing down the contrapositive. Then we'll call it a day and come back on Thursday, quantifying it, and then finally proving it. So again, we're focusing primarily on this part right here. The sentence above is just saying the domain of the values, x and y. We want to think of this part right here as P, x, y rational. Here's the if then for the implication going that way. Here's the Q, then x is rational or y is rational. So that's the original statement. But also this statement is even more complicated than it looks on its onset. Because there's an or right there, we have another idea we want to throw on the paper. When we go to negate x is irrational or y is irrational, we're also going to go back to section still 3.3 and use De Morgan's laws at the same time. So let's throw that in there. De Morgan's law says if we negate this line here, let's put in both on the notes, negation of this, that's going to be the not Q part right here in the contrapositive, is going to turn it into a conjunction, an and statement. So all of our careful work on logic was really so we could attack these problems, like we see here on example 5. The statement's hard to prove directly. It's hard to get started, but once we write down everything cleanly as the legitimate contrapositive, we'll be impressed by how fast the original proof actually goes, the resulting proof rather. So let's write this down all in paper finally. The contrapositive of the above statement would say, I'm going to ignore this part. This is just going to be the overall assumption for the domain of the numbers and focus on the if then. If we're starting in the contrapositive with this part, not Q, which means we negate this part right here. It's an or statement, which means we write it in as an and. So let's write that all together as if x is not irrational, that just means it's rational. Real numbers follow a dichotomy. They're either rational or irrational. So if I'm negating this, we're saying they're rational numbers. It's in the set Q. De Morgan's now comes in, flips the or to and. Y is irrational. Negate that. Negation is that y is in Q. So if x is rational and y is rational, then we need to negate P to get the full contrapositive. But negating this is not so bad. You just say, same process. Negation of x divided by y irrational just means x divided by y is rational. And I'll abbreviate to saying xy is in Q. So that's our statement. And notice that this one feels more intuitive, in my opinion at least. If you have two rational numbers and you divide like this with the assumption y is non-zero, so that this is defined, division of two rational numbers should stay rational. But what did this give us? Why is the contrapositive so critical? It's because the moment you say it's rational, you now have the algebraic hook. For defining both x and y, we can use algebra, work some stuff out, and conclude here by matching up the same form, just like with odd and even, x divided by y is still rational. So this right here is the superstar for this original statement, contrapositive. For me, it's one of my favorite proof techniques because it's kind of amazing how you can write a statement that looks very plausible, but feels almost impossible to prove directly as written. But just flip it around, use a logical equivalence, change the implication to a contrapositive, And suddenly, the most mysterious statement ever is very, very fast to prove. And we'll show that on Thursday. Looks like I went over. Sorry about that. Any last questions at all, folks? Just putting down the contrapositive on paper. Okay, well, thanks for your patience on getting through these tricky problems on proofs. They're definitely not easy. Sometimes it's hard to get through them. I appreciate all the questions as we went through these, and we'll be right back here when we come back on Thursday. We still have several other proof techniques to get through, so we'll make sure to take our time and care with each one of them. But have a great afternoon, folks. We'll be back to it next class. Thanks.